Hello, in this short video I have some additional questions on the analysis of a first order transfer function. So there's 4 questions for you to have a go at. So you can see there, consider the following first order transfer functions subject to a unit step input. So A, B, C and D. So you've got 4 different first order transfer functions. So what I want you to do in the questions is determine the following for each one of these transfer functions. The time constant and the system gain. So it'll involve putting each one of these transfer functions into the standard form for a first order transfer function. The next step then is to sketch the system response. And on the system response, I want you to label the final value of the system and the output values relating to 63.2%, 95% and 99% of the final value of the system.
So I'm now going to run through the 4 questions that you saw on the previous slide. So just to recap, the standard form of a first order transfer function is given by this. So GS for the open loop case, but it could be for the closed loop control system, is equal to K, which is the system gain, multiplied by 1 over tau, which is time constant, multiplied by S, plus 1. So question A, the transfer function is given by this, so 1 over S plus 1. So this is a nice easy one to start off with because it's actually already in standard form. So therefore, because it's already in standard form, therefore the system gain is 1. Okay, because there's a 1 value here. And tau, which is the time constant, is also a value of 1. So a nice easy one to start off with. So if we're looking in terms of this table here, so percentage outputs are 63.2%, 95%, 99%, and then the time in seconds, if we recall that for this percentage output, this is equal to tau, 95%, 3 tau, 99% is 5 tau. Obviously, because tau is 1, therefore these are equal to 1, 3, and 5. Because obviously 3, 1, 5, 1 is 5. Okay, so 1, 3, and 5. In terms of the output amplitude, it's Y. So Y in terms of, if you recall previous, well, we went through previously, I'll write these down. So 632, 0.950, 0.990, okay, multiplied by K, which in this case, K is equal to 1 for each one of these. So we know that the output amplitude is obviously effectively equal to the values that I originally just wrote down because K is obviously equal to 1. So that's nice and straightforward. So if we're going to then sketch this on the graph here, we know that the final value of the system, because the system gain gives us the final value, so let's just put a typical first order response in there. We know that the final value is an amplitude value of 1. We then, if we just put on 60, let's put on 63.2%, 95%, and then 99%. Okay, it's only a sketch, so don't worry too much. We know that 63.2% are at 1 second, 95% are at 3 seconds, and then 99% it's at 5 seconds. And then we can put on the corresponding value. So this will be 6, 3, 2. This one here will be 0.950. Then this one here, which is not so, I'm just going to put an arrow there, will be 0.990. Okay, and that there is your first question, question A. So you can see your system response, you can see the time, and you can see the time that it takes to get to these amplitude values. Okay, so it takes approximately, well, it takes 5 seconds to approximately get to the final value of the system. Okay, obviously that's 99%, but it's approximately near enough the final value of the system. So then if we move on to B, so B's slightly more difficult because what we need to do is we need to obviously get this into standard form. So because this is the highest value here, 6, what I'm going to do is I'm going to divide through by 6. And then what this will give me is 2 over 6. It'll give me 3 over 6. So I'm just going to I'll put 3 over 6 there to begin with. S plus 1. Okay, so that's now the form that I like. And then we do equal. And what I'm going to do is I'm just going to put 2 over 6 here. And then a 1 on top. and then I'm going to put 3 over 6, that's 0.5, s plus 1. And thereby you can see now that is in standard form. Therefore, k is equal to 2 over 6, and tau is equal to 0.5. Okay, 0.5 tau. K system gain is 2 over 6. So hopefully now you're starting to see how we get these into these forms that we're after. So again, if we're looking at this table, let's first of all fill this out. So 0 tau, in this case 0.5, 3 tau is 1.5, because 3 times 0.5, 5 tau, sorry. 5 tau is 5 times 0.5, which is 2.5. And then the output amplitude is, as usual, the relationship you expect. However, this time it's multiplied by k now. K is not 1, it's 2 over 6, which in this case is 0.2107. And then this one here would be 0.95 multiplied by 2 over 6, which is equal to 0.3167. And then 0.990 times by 2 over 6 is equal to 0.330. Put another 0 there just to be consistent. So what does this look like in the final, in terms of the system response? The final value is, because the system gain is going to tell us the final value, is 2 over 3. Okay, or you could put, I guess, you could put 0.333, I guess. It's up to you. And then in terms of, again, exactly the same idea, put on 63.2%, 95% at the final value, and then 99%. Okay, it's only a sketch, so that's going to be 0.5, 1.5, 2.5. Okay, so that's the time. And then these values here are 0.2107, 0.3167, and this one here, again, it's a bit difficult for me to get, 0.3300. So you can see in this particular case, it takes approximately 2.5 seconds to get to the final value of the system, where in this case, the final value of the system is oh no, sorry, I shouldn't have put 3 there, it's 2 over 6, or 0.333. Okay, sorry, slight mistake there. Right, then if we're moving on to then C. Okay, so if we're moving on to C, again, we want to put into the final, into the standard form. So we want these values to be here. So what I'm going to do is, I'm going to divide through by 3. And then this is again going to give me 1 there, and then 1 over 3s plus 1. Okay, again, it's nice. Therefore, k is equal to 1. So again, I like when k is equal to 1, it makes it a bit easier. And tau is equal to 1 over 3. Okay, k is equal to, or system gain is equal to 1, obviously, because the numerator value here is 1, and obviously we haven't moved anything outside. And then tau 1 over 3 because of that value. So then likewise, we fill out this table. So 0, obviously percentage output, 0, 0. Tau is just 1 over 3. 3 tau is 1. Okay. 5 tau is 5 over 3. And then in terms of the output amplitude, it's y times k. Okay, because k is 1. I'm not even going to bother working out the calculations this time because we did them previously. So it's just this relationship that you expect to see. So when the gain value is 1, you'll always see this relationship here. Okay, you'll always see this relationship and this relationship here. Obviously the time here depends on the time constant. So then let's draw the system response. So it's a first order system response, no overshoot. Final value 1. Let's again just put on 63.2%, 95, and then 99. Again, approximation sketch. My sketch isn't really, it's okay, but, and then in terms of time, 1/3, 1, and then 5 over 3. Right, and then in terms of the amplitude, it's going to be here 0.6320 and here 0.950 and this one here 0.990. So in this case it takes approximately 5 over 3 seconds to get to the final value of the system, or 99%, which is obviously a good approximation. So D is given by this transfer function. So obviously this coefficient here, because what we're normally looking at is this coefficient here, because we want to make this equal to 1. This coefficient here, so what I'm going to do is divide through by 2. And then that's going to give me 2 over S plus 1. And obviously because I've got this 2 on the top now, what I can do is I can just move that outside like that to put it into the standard form. Therefore, K is equal to 2 and tau is equal to, in this case, tau is equal to 1. Because obviously there's no, coefficient there would just be 1. Right, so in terms of this, then the table, so let's do 0. Tau obviously is now just 1. So for tau, 1 tau is just 1. 3 tau it's 3. And then 5 tau it's 5. Okay, nice and easy relationship there. And then now obviously the K value is 2. So if I just write these out, 632 multiplied by 2. Okay, because the Y output of the system multiplied by the gain, which in this case is 2. 0.950 multiplied by 2. 0.990 multiplied by 2. So in this case, this is going to, the product of that's going to give me this. Product of this is going to give me this. And the product of this is going to give me this. So in a similar manner, just draw what you expect a first order response to look like, approximately. The final value of the system is going to be 2 because the system gain is 2. So 2, voila. 63.2% approximately. And you probably notice in my sketches, you're probably thinking of the time axes, none of them look particularly great, but it's only a sketch. You could put maybe more numerical values through to get a better approximation, but it's all good. And then here, it's going to be 1, 3, and 5 seconds. Okay, for 63.2%, 95 and 99% these. And then the values in the amplitude are going to be 1.2640, 1.900, and then this one here, 1.980. And that really concludes this final question, where approximately it takes, to get to the final value of the system, it takes approximately 5 seconds in this case. So what you'll notice is when we're going through all these questions is putting the transfer function into standard form enables you to work out the final value of the system and also the amount of time that it's going to take to get to the final value of that system. And the only thing that's really varying is in terms of this column here, in terms of the time, and in terms of here, the output amplitude is varying as a subject of the system gain. Okay, so this is a useful little method just to kind of quickly get a hand sketch of a first order system response.